Good morning, or maybe good afternoon for those of you who are following us from Europe, and welcome to this PLAXIS webinar on modeling tunnel and rocks with PLAXIS. My name is Richard Vitas, and I am a senior advisor for PLAXIS, and today I will be assisted by Vincent, sales engineer at PLAXIS too. If you look at your dashboard, actually, you can see that you have the possibility to raise your hand and ask questions through the entire duration of the webinar. We strongly encourage you to do so and to drop any points you would like us to answer. Vincent will monitor the flow of questions and will answer them live as much as time permits. However, if some questions would remain unanswered, we will follow them up in a separate email afterwards. So don't worry, any question that will be raised during this webinar will be answered at some point. So this webinar will consist of two different parts. A very short and maybe for some of you straightforward overview of the most relevant features in PLAXIS for modeling tunnel in rocks in both 2D and 3D. And this presentation will be followed by a live demonstration of the multi-stage excavation, including rock bolts in PLAXIS 2D. So this is the content of my presentation. I will first give a few words about the tunnel designer in both PLAXIS 2D and 3D. Then I will give an overview of the available material models dedicated or particularly relevant for tunnel application. The third part of this presentation will be consisting of a short presentation of available structural elements in PLAXIS, and more particularly rock bolts. And finally, I will say a few words on different possibilities for modeling tunnel contraction. So the tunnel designer is now available in both PLAXIS 2D and 3D software packages. This tunnel designer, which is a dialog box, which is represented here on the right-hand side part of the slide, has some strong similarities with the PLAXIS modeling workflow, in the sense that it contains modes like cross-section mode, property mode, phases mode, and a trajectory mode. The last two modes are only available in PLAXIS 3D. It also offers rulers, grid, origin, and snapping mechanism to ease the definition and the selection of the constitutive objects in your model. We do also offer multiple selection tools by means of drawing selection window. We are also offering the well-known right mouse button context sensitive menu, which presents for any selected object the relevant actions only which can be considered for such selected object. And finally, we do offer intersection facilities as well. So the most relevant features of the tunnel designer are the following one. The possibility, of course, to create tunnel cross-sections, but also to import them. We do have options to add thick lining, benches, and so on. And also the possibility to assign all relevant structural and material properties that belong to the tunnel. So all properties must be defined within the tunnel designer, and which is particularly convenient, to ensure consistency when you keep on editing your tunnel for doing modifications. We do also for 3D offer the possibility to create straight, plunging, or arching tunnel trajectories, as well as defining tunnel sections in 3D by slicing the trajectory. So the cross sections can be defined either entirely or half if one wants to take into consideration symmetry conditions eventually, and this will be defined for the tunnel shell in the first place. Then, based on this tunnel shell, thick lining, benches or sidewalls could be defined by, for instance, offsetting the tunnel shell. And as I was saying earlier in my presentation, it is also possible to import DXF and DWG cross-sections. The tunnel designer is also the place where properties can be defined and where you will add properties to the tunnel. Properties could be plate, interfaces, loads, contraction, eventually boundary conditions if relevant. And finally, for a 3D model, we do offer trajectory and slices modes. So those modes are meant for the definition of the slice from the trajectory into sections to be excavated, where the user can divide the trajectory by a number of segments or by entering a segment thickness. So a practical example of using the tunnel designer in 3D will look like this one, where you see a cross-section has first been defined containing two side excavations on which part of the tunnel section, and a trajectory consisting of a 90 degrees bend. Finally, after generation, this is how the tunnel will look like in PLAXIS 3D. So this was the first part of this presentation. Now, at this stage, I would like just to give a very brief overview of the different material models available in PLAXIS 2D and 3D. The first one I like to mention is the Shotcrete model. The Shotcrete model is available as a so-called user-defined soil model. And the Shotcrete model has the following capabilities. First, the possibility to take into consideration strain hardening or softening in both compression and tension, which is particularly relevant for modeling concrete material in general, Shotcrete in particular. So worth mentioning that this Shotcrete model could also be used for the purpose of modeling concrete, mature concrete. Concrete being considered as a mature Shotcrete, basically. For the particular case of modeling Shotcrete, we also offer in the model time-dependent strength and stiffness, which could be entered as a function of time. And finally, the model will also take into consideration inelastic strain due to shrinkage and creep mechanism. So this is a brief summary of the Shotcrete model. The next model I like to briefly present in this presentation is the Hoek-Brown model. The Hoek-Brown model, it's a relatively simple model from a theoretical point of view. It is a linear elastic, perfectly plastic behavior with Hoek-Brown failure criterion. I would say this model has a lot of similarities with the Moore-Coulomb model, except that the Moore-Coulomb model considers a linear strength as a function of the mean effective stress, whereas the Hoek-Brown failure criterion considers a nonlinear relationship between shear strength and mean effective stress, which is described by the Hoek-Brown failure criterion. So the failure criterion for the Hoek-Brown will be defined thanks to the parameters of the Hoek-Brown failure criterion, which are the intact uniaxial compressive strength, the geological stress index, the intact rock parameter, and the disturbance factor. Another model well suited for the modeling of rock is the jointed rock model. The main characteristic of the model is the consideration of transverse linear anisotropic elasticity, basically the possibility to enter two different stiffnesses, two different Young's modulus in two perpendicular directions, according to stratification most of the time of the rock. And then additionally, the user can define up to 3 predefined directions along which and only along which plasticity in elastic strain could develop according perfect Coulomb plasticity, with for each predefined direction independent set of cohesion, friction angle, and tensile strength. So here I can give very simple application of this model when considering circular excavation in a rock mass using respectively 3 different angles of the failure direction of respectively 0 degrees, 90 degrees, and 45 degrees. And what you see is the development of plastic points, which are predominantly developing along this direction. Still, I would like you to bear in mind that it's still a model which is developed in the framework of a smeared approach. So there is no consideration of possible, I would say, of possible distances between rock joints along which failure could occur. It's still a smeared approach. So we are making the same consideration of the model regarding failure at each integration point. And the last model I like to briefly talk about is the swelling rock model, also available as a user-defined soil model. This model is meant for the modeling of swelling clays and anhydric rock. So the main features are the following one. Like the jointed rock model, we are also offering transverse autotropic elastic stiffness because this is something relevant for modeling rock mass. Additionally, we do have elastic, perfectly plastic behavior based on the Moore-Coulomb failure criterion. So with these two features, this model would resemble to an orthotropic Moore-Coulomb model. The particularity of this model is the consideration of a swelling strain, a swelling inelastic strain, which depends on both the stress and the time based on the swelling law that the user can define. The third part of this presentation is related to structural elements and modeling rock bolts. In PLAXIS, we are offering the following set of structural elements. Plate elements for tunneling shield and lining, beam elements, especially relevant for tunnel guiders, for instance, interface elements for the consideration of nonlinear soil structure interaction, and finally, embedded beams for soil reinforcement in tunnel application, rock bolts. I'm not going to discuss the details of the first 3 types of elements, plate, beam, and interfaces. It's just because I really would like to focus on tunneling in rock. So I will slightly elaborate on the modeling of rock bolt at this stage. So soil reinforcements, like soil nails or rock bolts, can be modeled by means of beams or embedded beams. Beams are based on milling theory. So what we do is that we are considering linear elements which can support normal action, bending moment, and transverse shear. Additionally, the user has the possibility to define an elastoblastic behavior, so provide a maximum value regarding forces and bending moments than the element can withstand. But still, those elements, beams elements, will always be assumed to be rigidly connected to the surrounding soil. So they will always be able to transfer shear in the soil until eventually soil would fail. This is because of this limitation that the embedded beam has been introduced. The embedded beam elements is a combination of a beam with the exact same property as mentioned before and some very specific coupling springs to the surrounding soil. So the nodes of the beam are no longer shared with those of the soil. They are separated, and in between, special nonlinear spring elements are being introduced. And the particularity of the springs is that the user can specify skin and tip resistance. The tip resistance is mostly relevant for pile modeling. For rock bolts, they will be usually set to 0. The skin resistance, however, is a nice feature. It enables the user to limit the amount of shear that the rock bolt can transfer into the soil. As long as the shear traction developing between the beam and the soil will remain under the skin resistance, then the rock bolt will transfer shear into the soil. When this value of the skin resistance will be reached, then the beam element will start sliding inside the soil and no longer able to transmit any further shear stresses, leading most likely in your model to stress redistribution with surrounding elements which still do have some remaining capacity. So this briefly presents the modeling of rock bolts in PLAXIS 2D. On the left side, you see the modeling, which is, by the way, going to be the model I will present later on in PLAXIS 2D. And you see the purple lines representing the rock bolt. And on the right part of the screen, you do see the set of material properties that must be defined for the embedded beam. We do have, in the first place, property relevant to the beam here. So in terms of stiffness, unit weight, and cross-section properties, here diameter for a plain circular pile. And then later on, the possibility to define the skin resistance and the base resistance eventually, should you be modeling a pile. And this is the place where you will specify the variation of the skin resistance along the length of the element. So this finally brings me to the last topic of my presentation related to tunnel contraction. Tunnel contraction in PLAXIS can be introduced in two different ways. First, in the tunnel designer by means of a prescribed strain along the tunnel lining. And the prescribed strain will be automatically defined by PLAXIS based on the value of the contraction that the user will input. And this contraction will be defined as the ratio between the change in area over the initial area of the tunnel. This input will then be converted into a autoradial strain, prescribed strain to the tunnel, and then apply to your model in the corresponding phases. One should note at this stage that the tunnel contraction value that you have specified can be activated in any phases, but also changed in any phases. And alternatively, you could specify the tunnel contraction not as a prescribed strain onto the tunnel lining, but as a prescribed target volume strain onto the soil to be excavated. So it's a slightly different method, but you can also apply a volume contraction into the soil mass, which is supposed to be removed, and leading also to tunnel contraction, should you be willing to investigate the effects on subsurface subsidence or stress redistribution to the existing buildings. So this ends up my presentation, my very short presentation. Again, I just here wanted to give a very brief, short overview of the possibilities and the features that we are offering. Should you be willing to receive more information on those aspects, please feel free to ask sales or support. The second part of this presentation is now dedicated to a live demonstration on PLAXIS 2D on the geometry I was presenting before. So I'm now opening PLAXIS 2D. I've already started before starting this webinar. So this is a model which for the time being does not contain any element. So the first action that will be undertaken will be the creation of the soil geometry within the soil mode. This will be done by adding a single borehole by clicking on the Create Borehole facility. We click on the borehole, place the borehole here at 0, 0, and define the soil geometry in terms of stratigraphy at this location. So the soil layer, the unique soil layer for my model here, will be going from 0 to -60. Okay, so you see, and this immediately generates a soil polygon for which no properties have been attached yet. I will consider this soil mass to be initially dry by setting up the waterhead at the bottom of my model at -60. And finally, I will need to attach material properties for that soil volume. So this will be done by clicking on Materials, which will open the Material Set dialog box like this. And here I will create a new material in the Soil Mont-Coulon dialog box. So here I will call this rock. I will give unit weight of 25. I'm working with SI units here. The parameter will be the following one. So stiffnesses parameter will be 1 million kilopascal, so 1 gigapascal, Poisson's ratio of 0.2, a cohesion of 50 kPa, and a friction angle of 33, as well as some little tiny tensile strengths of 1 kPa. And finally, for the generation of the initial stresses, which is always very relevant, I will set it up to 0.5. Okay. And this will be the set of properties that I will be considering for that particular example. And I will finally drag and drop it to the only constitutive layer of my model. Okay. And here we are. I have now generated the soil geometry for the problem I am about to address. So I'm going now into the structures mode, which is the second mode, where I will now define the tunnel geometry. So the tunnel geometry will be defined through the tunnel designer, which is located here. You see, this is how one can create a tunnel in PLAXIS. So I do click the Create Tunnel, and I will choose an insertion point at -35 here, and then click. which will bring me into the tunnel designer, like you see now on your screen. The shape type here would be free because it will be made of an assembly of arcs. However, I will specify that I'm only interested in modeling the right half due to symmetry conditions I am considering for this particular problem. Then I will go to the segment tab, the second tab here. I will click on segment. And this is the place where I will define the constitutive segments for the tunnel. So add, the add segment button located here, and needs to be selected once, which will create an arc, which by default is always aligned in PLAXIS. I will change the nature of the segment to arc, and then give the corresponding properties for this arc. So a radius of 17 meters and a segment angle of 20. Like this. This corresponds to the first segment. I will then add a second segment, clicking again on the Add button. This will also be an arc with a radius of 3.5 meters. And this corresponds to the second arc. I will add a third arc, still clicking on the Add button, which will also be an arc of 6.5 meter radius and segment angle of 35. Okay, and then finally I will close this cross section by selecting the extend to symmetry axis. The extend to symmetry axis will generate an arc with the following properties. The arc will start at the last created point up to the symmetry axis, and it will also ensure continuity of the tangent at this point and a tangent equal to 0 at that point along the symmetry. So this is how it will be drawn by clicking on the extend to symmetry axis. At this stage, we can consider that the outer contour of my tunnel is defined. So I will now enter the subsections to define the inner contour. So the subsections list is also empty because no subsection has been created so far. I will, in the same way as I was defining segments, create subsection by clicking on the Add button here. I will create a first subsection, which will be an arc with a relative start angle of 180, a segment angle of 180, and a radius of 8 meters. And then I need to offset this arc properly by entering the proper offset here, so which would be 12 and 13. So this is the construction line, and this is how the side excavation, along which the side excavation will be performed. I will add another line to now make a separation between the top heading and the invert. So I will create a line, I will offset it 5 meters upwards, and I will specify a length of 7 meters, like this. So now I have just defined two construction lines that will be used for for representing the inner contours. And then finally, I will select all the relevant contours and intersect them with one another using the intersect segments command. You see the intersection has now been performed, and I can remove the unnecessary subsections like this one, and this one. So at this stage, we can consider that the geometry of the tunnel section is terminated. We will now define the relevant properties for it. So I am now going into the properties mode, where I see a list of all the slice polycurves which has been generated. Here, 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 and there, etc. First, we will create plates at the location where Shotcrete is expected to be used. So this will be done by first selecting the relevant polycurves, like this, right mouse click, and here choose Create Plate from the drop-down menu. Okay? And note those plates which have been created here must be given the right set of properties. Initially, by default, those properties are not being assigned and must be defined. So this will be done, and clicking on the plus button to define the property of the plate. So in that particular case, I will name this one Shotcrete and give relevant property for the normal stiffness and for the bending stiffness. Okay. We may also enter the Poisson's ratio and eventually, if one wants to, relevant weight for this application. The Poisson's ratio is 1.15. So this is the set of properties I want to use for my Shotcrete. So I will assign it here. So this is done. Okay, no, I can see that I've given some properties for the Shotcrete. And then to finish, I will define for the outer contour a set of interface elements. Right mouse click again, and here create interface. This way. Now the tunnel geometry is fully defined with the respective properties. So what I will do, I will click on generate and generate the tunnel. So like this, generate and close. And you see now that the tunnel geometry has been created. So to finish with the structural element, we must now include the embedded beam, the rock bolts. So the rock bolts could be created using this command here, line, create embedded beam rope. And then we could simply select a begin point and then an end point. Okay, but this is not the way I'm going to define it here, because there is quite a number of bolts and I need to figure out all the coordinates. So what I will do, because the coordinates are already known, I have in fact worked out from the coordinates the respective command to generate the. Okay, so what I will do at this stage, I will simply select the relevant set of commands that has been created in Excel quite easily. I will copy them and finally paste them in PLAXIS 2D using the command runner, which can be accessed from the run commands. And here I can paste those commands, which are now given here. And I can just run them, which will automatically create the relevant set of rock bolt. Still, if you look carefully, it is difficult to exactly match the coordinate of the beginning point right onto the outer contour of the tunnel. So for that purpose, we will snap those beginning points to the outer contour by using the trim extend functionality. This way, and now you see the embedded beams are rigidly connected to the outer contour. We can repeat this operation for all the rock bolts this way. Now we are sure that the rock bolts are properly connected to the tunnel liner. Finally, we need to attach the set of properties for the embedded beam. So we'll first select them like this. Look into the Selection Explorer, Material, not a sign, of course. Click on the plus sign right here to create a new set of material and enter a relevant set of properties for the rock bolts. So 206, 78 kilonewton per cubic meter, and a diameter of 25 millimeter. This is for the property of the beam. And then for the skin resistance, I will assume a uniform skin resistance of 63 kilonewton per meter over the entire length of the rock bolt. So if you multiply the skin resistance by the length of the beam, this will give you the pull-out force of the anchor. And that's it. So now, at this stage, the geometry of the problem is fully defined. So this will bring us to the mesh mode. And in the mesh mode, we will we will generate the mesh. I will specify some refinement first at places where large stress gradients are expected to develop. So I will select the 3 soil cluster corresponding to the tunnel excavation, and I will set the coarseness factor to 0.25, which means that I want locally to use an element size which is 4 times less than the average element size. And I will repeat this operation for the line supporting the rock bolts. And here specify a coarseness factor of 0.1, so mesh which is 10 times smaller than the average element size. Once proper mesh refinement has been specified, I will generate the mesh. And I will view the mesh by clicking on View Mesh. And this is the mesh which has been obtained. So the first thing you see here is this gap here, which is introduced for the sake of locating precisely where the interfaces are defined. But in reality, in the reality of the mesh, such a gap does not exist. So you can scale this down. And this is more how your mesh looks like. And if you keep on zooming in, of course, you will still see a little tiny gap here. Another remark is that it looks at first that the coarseness of the mesh is just average. But if you look carefully, do not forget that PLAXIS are using high order elements, fourth order elements. So if you look at the node, and you display the node, we still have here a relatively high node density. So in fact, the mesh that is being considered here is in fact extremely accurate and extremely fine. PLAXIS do not use linear element. We are using fourth order interpolation element. So I will close this, and which will bring me back to the mesh mode. And now I will enter finally the stage construction to define the relevant construction stages for my model. So for the initial phase, where I need to define the right state of initial stresses, PLAXIS consider that all structural elements are deactivated and all soil clusters are activated, which is in that case exactly what I want to consider. So for this initial phase, there is nothing particular that must be done. So I will just activate this phase and move into the next phase, phase number 1. In phase number 1, I will perform the site excavation. So I will first select the soil cluster located at the side of the tunnel, and I will deactivate it this way. But because we are dealing with a 2D model representing a 3D situation, arching effects that are supposed to develop in the longitudinal direction cannot be properly addressed here. So this is usually addressed in a 2D application by using by considering a sum M stage which is not equal to 1 but equal to some lower value, such that at the end of the phase there is still some force, some soil pressure remaining onto the side of the excavation. So this can be done in PLAXIS by changing here the sum M stage factor 2.5, meaning that at the end of this phase there will still be 50% left of the initial soil pressure. Okay. I will then create a new phase, phase number 2, where I will activate the rock bolts. This way. And for this phase, I also want to maintain at the end of this phase some of the initial soil pressure that was applied on this contour, 25% in reality. So this will be done by setting up the sum M stage again to 0.5, because we have already 50% left from the previous phase. So if we take another 50%, then we will have 25% left over. And then finally, for phase number 3, we will include the Shotcrete by selecting plate element this way. Okay. I will remove this one and this one. So I want to select those elements. From the Selection Explorer, I can activate both the plates and the corresponding interfaces. And this will define. So those are the 3 phases that are required to perform the first excavation stage. And I will repeat the exact same set of 3 operations for the excavation of the heading. So it first had phase number 4. I will select the soil, I will select the plates, and I will deactivate them. And I will also set the sum M stage to 0.5 to remove only 50% of the out of balance force. I will add a new phase, and now I will select the top rock bolts and I will activate them from the Selection Explorer here on the left. And also set the sum M stage to 0.5, so that at the end I still have 25% left over from the initial out of balance force before I perform the excavation. And finally, in the last phase, I will activate the plate element like this and the corresponding interfaces. So this was for the second excavation, and to finish I will perform the excavation of the invert. I will again create a new phase, phase number 8, and I will select these two objects, the Shotcrete and the invert, and I will deactivate them this way. Of course, without, again, forgetting to set the SUMM stage 2.5. And the last phase, finally, will consist of activating the last part of the Shotcrete lining, like this. From the Selection Explorer as well. So model definition is now complete, and calculation can be run. So which will be done by using the calculate button here. So I click on calculate, and the calculation will be started. So the calculation here will take a bit less than 1 minute. On my laptop, it's just a standard laptop. There is nothing exceptional. And PLAXIS will then compute each phase iteratively. So this is phase number 3. Phase number 4. Phase number 5. Phase number 6. Seven. And finally 8, the last phase. So the calculation is now terminated. We can take a look at the model results by selecting the View Calculation Results. Here we are. So by default, PLAXIS always presents the deformed shape for the last calculated step. Mind here that deformed shape, deformed mesh is given with a magnification factor of 100, as shown here. Okay. So interesting results here would consist in first taking a look at the settlement, the vertical displacement. So this can be accessed from the Formations menu, Total Displacement, UI, like this. And then the user can query the value using the inbox. So you see that at the top, the total displacement is about 12 millimeter, something. The value appears in the inbox. We can also draw a cross-section and evaluate the profile of the settlement at the top. And we can also then start moving in up and down to also evaluate it at different locations, like this, all the way side, and eventually at the bottom when we start to see soil heave, actually. And as we further go down, then the heave starts diminishing until it fully vanishes. Okay. Another interesting output here would be the evolution of the plastic strain to see where soil is shear failure develops. So to ease the visualization here, which is not very to see the visualization, I can hide the embedded beam, the rock bolts, as well as the soil contour. The element contour, sorry, to get rid of the element contour. This will so ease the view. And then I can see the development of this plastic strain along all faces, you see. I'm now moving back. So this is the initial situation, and this is how the plastic strain will develop in the soil mass as the excavation further progress. Okay. So this was for the soil. We can also take a look at the results for the structural element by selecting them in the first place, like dragging a window, and then select first the embedded beam corresponding to the rock bolt. Those are the embedded beam results. And for instance, one can look into the axial normal forces that develop into this beam element, maybe scaling this down a little bit. So this gives how the forces develops into the rock bolts. And here as well, we can start moving through the different phases and see how they develop as the excavation progress in the model. And maybe last interesting results would be to evaluate the normal forces onto the lining by first selecting the Shotcrete like this plate view, which will bring me to the structure mode. And here I have the possibility to represent either the normal forces for the different construction phases that have been defined for this model. So this ends up my presentation and this webinar. I don't know what the status is regarding answering the question. Should you be willing to receive some more information about what has just been presented, or whether you want to you have any other questions related to how we could eventually further help you with your modeling, do not hesitate to contact our sales department or our support department. You can also check our website, which will provide an overview of regular events that we are organizing worldwide, and especially training courses that are being organized on different topics, both in Europe but also in the US. And finally, I would like to thank you for joining this webinar and for staying with us during the last hour. It's greatly appreciated, and we are looking forward meeting you again for the next webinar that we will organize very soon. So we'll end up this this session now, and I would like to wish you a very nice day. Goodbye.